Look up at the night sky on a clear evening, and you'll see a river of stars stretching across the darkness, our home galaxy, the Milky Way. It's a sight that's inspired wonder for thousands of years, a shimmering band of light that seems almost close enough to touch. But here's the truth. What we see is just the faintest whisper of something far grander, far stranger, and packed with secrets we're only beginning to unravel. For all its familiarity, the Milky Way hides countless mysteries in its swirling arms, some so bizarre they'd feel at home in a science fiction novel. And today, we're diving deep into the cosmic shadows to uncover them. Think you know our galaxy? Think again. Behind those familiar stars lie forces and phenomena that defy logic. Black holes with the mass of billions of suns lurking unseen, vast clouds of antimatter drifting through the void, even entire streams of stars stolen from other galaxies, all of it woven into the fabric of the Milky Way. And that's just the start. Some of these secrets are tucked so close to us they've been hiding in plain sight for centuries. Others stretch the limits of what we thought possible, rewriting the rules of physics itself. This isn't just a tour of cosmic oddities, it's a journey to the edges of human understanding. Every discovery we make about our galaxy peels back another layer of the universe's grand design, revealing just how little we truly know. So if you're ready to have your mind stretched by the unseen wonders spinning right above us, stick around, because by the end of this, you'll never look at the Milky Way the same way again. But the Milky Way holds its greatest secret where we can't even see it, an invisible giant lurking in the darkness. Wrapping around our galaxy like a ghostly embrace, there's a vast halo of dark matter stretching hundreds of thousands of light years beyond the last visible stars. You won't spot it through any telescope, yet it outweighs everything else in the Milky Way combined. Picture this: every star, planet, and cosmic cloud we can observe accounts for just 10% of our galaxy's mass. The rest, it's all hidden in this mysterious, unseen structure, bending space itself with its gravity. Scientists first pieced together its existence not by seeing it, but by watching how stars move at the galaxy's edge. Instead of slowing down as expected, they race around the Milky Way's center far too fast, like marbles spinning impossibly fast on a plate without flying off. The only explanation, a gravitational grip from something invisible holding the entire galaxy together. That's the dark matter halo at work. Its pull so immense it dictates how our galaxy spins and even shapes its destiny. And here's where things get even stranger. While we can't see dark matter directly, its presence warps the fabric of space-time, bending light from distant galaxies like a cosmic magnifying glass, an effect called gravitational lensing. Astronomers use these subtle distortions like fingerprints, mapping the halo's ghostly contours. What they've found defies imagination. This halo isn't a smooth cloud but a dynamic web of filaments and clumps, a hidden skeleton around which the Milky Way formed billions of years ago. Without it, our galaxy wouldn't exist as we know it. Stars would have scattered into the void long ago. So next time you gaze at the Milky Way, remember, those glittering stars are just the surface. The real cosmic heavyweight is the invisible force holding it all together, silent and unseen, yet more powerful than anything we can observe. The Milky Way isn't just a serene island of stars, it's a cosmic predator with a violent past. Billions of years ago, our galaxy didn't grow quietly. It feasted. Like a celestial titan, it ripped apart smaller galaxies, absorbing their stars and rewriting its own history in the process. And the evidence, it's written in the very motion of the stars around us. Take the Gaia sausage, no, not a galactic snack, but the remnants of one of the Milky Way's most dramatic meals. This strange, sausage-shaped cluster of stars orbits the galactic center at odd angles, like a group of rebels refusing to fall in line. Astronomers piecing together data from the Gaia Space Telescope realized these stars weren't born here. They're survivors of a dwarf galaxy torn apart by our Milky Way's gravity between 8 and 10 billion years ago. The collision was so colossal it didn't just add stars, it reshaped our galaxy's core, leaving behind a telltale imprint in the way these stars move. But the Milky Way's appetite isn't just ancient history. Right now, it's in the middle of another galactic feast. The large and small Magellanic Clouds, those faint smudges near the southern sky, are being slowly pulled apart. Streams of their stars already stretch across space, forming a ghostly bridge as our galaxy siphons them away. And in the distant future, even the mighty Andromeda Galaxy will collide with us, sparking another cosmic merger. What's astonishing is how we've uncovered this violent past. Stars remember their origins, moving in patterns that reveal where they came from. By mapping millions of stellar motions, astronomers have turned the Milky Way into a forensic crime scene, piecing together a history of galactic cannibalism written in the stars themselves. So when you look up tonight, remember, those glittering lights aren't just neighbors, they're witnesses to a drama billions of years in the making. Deep in the Milky Way, about 4,000 light-years from Earth, spins a cosmic oddity that puts every jewel on our planet to shame. Meet PSR J1719-1438b, a world so dense, so extreme, that it's quite literally a diamond the size of a planet. This isn't poetic exaggeration. Under unimaginable pressure, the carbon-rich core of a dead star has crystallized into a celestial gemstone, one that would make even the most extravagant billionaire blush. The story of this diamond planet begins with stellar violence. It orbits a pulsar, a rapidly spinning corpse of a massive star that went supernova. When that explosion happened, the outer layers were blasted into space, but the core remained, collapsing into an ultra-dense remnant. The pulsar's companion, once a star itself, wasn't so lucky. Stripped of its outer layers by the pulsar's gravity, what remained was a carbon-rich husk crushed into submission. Under pressures millions of times greater than Earth's atmosphere, that carbon didn't stand a chance. It crystallized into diamond, forming a planet-sized jewel hurtling through space. Now let's talk scale. This diamond planet isn't just a sparkling pebble, it's roughly 5 times Earth's diameter, yet contains nearly the mass of Jupiter. Crunch those numbers and you realize how absurdly dense this thing is. If you could chip off a piece the size of a sugar cube, it would weigh more than a car. And the value, forget calculating it in dollars. The entire diamond planet would outweigh all the precious gems ever mined on Earth by quadrillions of times. But here's the kicker, this isn't the only one. The universe loves extremes, and astronomers suspect diamond planets may be more common than we thought, especially around pulsars. They're the ultimate cosmic bling, forged in the heart of stellar destruction. So next time you see a diamond ring, just remember, there's a world out there that puts it all into perspective. Somewhere beyond the Milky Way's glittering disk, an invisible force is reeling us in at staggering speed. 14 million miles per hour to be exact. That's how fast our entire galaxy, along with hundreds of others, is being dragged toward a cosmic phantom known as the Great Attractor. And here's the twist, we can't even see what's pulling us. This gravitational behemoth hides behind what astronomers call the zone of avoidance, a region of space obscured by thick dust and stars from our own galaxy's bulge. It's like trying to spot a lighthouse through a blizzard. For decades, this blind spot kept the Great Attractor's true nature shrouded in mystery. Even now, with advanced infrared and radio telescopes piercing through the cosmic fog, we've only glimpsed fragments of the story. What we do know is terrifying in scale, a gravitational anomaly so powerful it's bending the motion of entire galaxy clusters, including our own local group. One leading theory suggests this colossal pull comes from the Norma cluster, a dense gathering of galaxies about 250 million light-years away, where mass equivalent to tens of thousands of Milky Ways clumps together. But there's a problem. The math doesn't quite add up. Even that immense concentration of matter shouldn't produce such an extreme tug. That's led scientists to suspect something even grander lurks beyond it, possibly part of a vast supercluster complex stretching across the universe's filamentary web. Then there's the darker possibility. Some researchers propose the Great Attractor might be a sign of something beyond our current cosmological models, a flaw in our understanding of gravity itself, or evidence of exotic physics playing out on scales we're only beginning to comprehend. Every new observation peels back another layer, revealing just how much we still don't know about the forces sculpting our cosmic neighborhood. So while we hurtle uncontrollably toward this enigmatic region, one thing's certain: the universe still holds cards it hasn't shown us. Our solar system isn't just drifting aimlessly through the Milky Way, it's on a grand, looping journey around the galactic center, a cosmic carousel ride that takes an almost incomprehensible amount of time to complete. Picture this: from our vantage point here on Earth, the sun appears to rise and set in a predictable rhythm, marking the passage of days and years. But zoom out far enough, and you'll see our entire solar system is tracing a much larger path, one that takes a staggering 230 million years to finish just one lap. Astronomers call this a galactic year, and it's a reminder of just how vast the scales of space and time truly are. To put that into perspective, think about Earth's own history. When dinosaurs first roamed the planet around 230 million years ago, our solar system was in roughly the same position within the Milky Way as it is today. That means in all the eons since, through the rise and fall of countless species, the shifting of continents, and the entire span of human civilization, we've barely moved an inch on the galactic clock. In fact, since the Milky Way itself formed around 13.6 billion years ago, our Sun has completed only about 20 full orbits. That's it. 20 trips around the galaxy in the entire lifespan of our cosmic home. What's even more mind-bending is how much the galaxy changes during each of these galactic years. Stars are born and die in massive supernova, nebulae collapse into new solar systems, and entire regions of space are reshaped by gravitational interactions. The Milky Way our ancestors orbited 230 million years ago wasn't quite the same as the one we see now. Some stars have drifted away, others have been consumed by black holes, and new structures have formed in the great spiral arms. And here's something to ponder: where will Earth be on our next lap? In another 230 million years, when the Sun carries us back to this same point in space, our planet might be unrecognizable or even gone. The forces shaping our galaxy operate on timelines so vast they dwarf human history entirely. So the next time you look up at the night sky, remember, you're not just standing on a planet. You're a passenger on a voyage so immense, its full scope is almost beyond imagination. Most stars in the Milky Way follow orderly paths, dancing gracefully around the galactic center like dancers in a cosmic ballet. But then there are the rebel stars moving so fast they're escaping the galaxy entirely. These are hypervelocity stars, cosmic outlaws flung into the void at speeds topping 1.5 million miles per hour. And their origin story, it reads like something straight out of a gravitational thriller. Take He 0437-5439, a blue giant streaking through intergalactic space at over 1.6 million miles per hour. By all rights, this star shouldn't exist where we found it. Its age, composition, and location tell a contradictory tale. Born roughly 30 million years ago near the galaxy's core, this star somehow ended up hundreds of thousands of light years away in the galactic halo, far beyond where stars that young have any business being. The math just didn't add up until astronomers pieced together the culprit: our supermassive black hole, Sagittarius A star. Here's how the cosmic crime unfolded. Billions of years ago, a binary star system ventured too close to the black hole's deadly grip. In a gravitational slingshot maneuver straight out of celestial physics, one star was captured while the other was hurled outward at unimaginable speed, like a stone from a catapult. That ejected star, E0437-5439, became a runaway, carrying the energy of that violent encounter with it. The kick was so powerful it broke free from the Milky Way's gravity entirely, destined to drift alone through the darkness between galaxies. But the mystery deepens. Normally, stars this fast should be ancient, their speed built up over eons of galactic interactions. Yet this one is relatively young, its blue glow betraying its fiery youth. Some theories suggest it might have been part of a triple star system, adding another layer of chaos to its origin story. Others propose it could have been born in a dwarf galaxy torn apart by the Milky Way, then later ejected by our central black hole. Regardless of its exact past, one thing's certain: this star is a testament to the sheer violence lurking at the heart of our seemingly serene galaxy. So while most stars live out their lives in quiet orbits, remember, some are born to run, catapulted across the cosmos by forces we're only beginning to understand. And somewhere out there, right now, another star might be getting ready for its own one-way ticket to infinity. The Milky Way isn't just a swirling mass of stars and gas, it's threaded with invisible forces powerful enough to sculpt entire galaxies. Hidden between those glittering arms, a colossal magnetic field weaves through space, stretching hundreds of thousands of light-years like an unseen spiderweb. This isn't some faint background hum. It's a dynamic force strong enough to steer cosmic dust, bend the paths of charged particles, and even cradle newborn stars in its grip. Scientists mapping these fields with radio telescopes have uncovered something extraordinary: delicate filaments of magnetic energy crisscrossing the galaxy, some so vast they dwarf our entire solar system. Picture rivers of invisible energy, their structure revealed only when cosmic electrons spiral along their length, emitting radio waves we can detect. These filaments aren't random. They form intricate patterns, often aligning with the Milky Way's spiral arms or stretching like bridges between regions of intense star formation. What's truly astonishing is how these magnetic fields act as cosmic architects. Inside stellar nurseries, those dense clouds where stars are born, magnetic pressure rivals gravity itself in shaping collapsing gas. Without these fields, stars might form chaotically. Instead, the fields channel material into orderly streams, guiding stellar birth like invisible hands molding clay. Some theories even suggest these forces might explain why stars often emerge in clustered families rather than isolation, with magnetic ropes bundling gas into multiple dense knots simultaneously. But the mystery deepens when we zoom out. These galactic fields might not stop at the Milky Way's edge. Observations hint that magnetic filaments could connect galaxies across the cosmic web, like threads in a tapestry spanning the universe. If true, it would mean our galaxy's magnetic heartbeat is synchronized with forces far beyond what we can see, an idea that blurs the line between local physics and the large-scale structure of everything. So while we often marvel at the Milky Way's visible beauty, remember, its true power might lie in the invisible. Those magnetic threads aren't just decorations, they're part of the galaxy's hidden scaffolding, shaping everything from the birth of stars to the way our cosmic neighborhood fits into the universe's grand design. Our galaxy should be drowning in neighbors, countless dwarf galaxies swarming around it like bees around a hive. According to our best models of cosmic structure, the Milky Way's gravitational pull should have collected thousands of these tiny satellite galaxies over billions of years. Yet when astronomers tally them up, the numbers don't add up. We've found barely a few dozen. This glaring mismatch between prediction and reality is known as the missing satellite problem, and it's one of the most persistent headaches in modern astrophysics. The mystery stems from our understanding of dark matter. Simulations show that the Milky Way's massive halo of invisible matter should have trapped hundreds, if not thousands, of small, dark matter clumps as the galaxy formed. Each of those clumps should have pulled in gas and stars, becoming visible dwarf galaxies orbiting our own. but when we look, the cosmos feels oddly empty. Some of these missing satellites might simply be too faint to detect after all. Spotting a dim, spread-out cluster of stars against the Milky Way's glow is like trying to pick out a single candle flame in front of a floodlight. Then there's the tantalizing possibility that dark matter behaves differently than we think. What if it's not as sticky as our models assume? Some theories suggest dark matter particles might interact with each other in ways that prevent small clumps from forming, leaving fewer seeds for dwarf galaxies to grow. Others propose that early radiation from the first stars might have ripped gas away from these potential galaxies before they could fully develop, leaving them starless and invisible. But here's the twist: recent discoveries might be turning the problem on its head. Ultra-faint dwarf galaxies, some with only a few hundred stars, have been spotted lurking at the Milky Way's edge, so ghostly they were missed for decades. Could there be hundreds more hiding just beyond our current telescope's reach? Or is the real answer even stranger, hinting at gaps in our cosmic theories that we don't yet understand? The missing satellite problem isn't just a quirk of galactic accounting. It's a challenge to our fundamental picture of how structure forms in the universe. Every undetected dwarf galaxy is a question mark, forcing us to reconsider how dark matter shapes the cosmos. Until we solve it, we're left with a humbling truth: the Milky Way story might be missing entire chapters we don't even know how to read. Rising from the heart of the Milky Way like two colossal hourglasses, the Fermi Bubbles stretch 50,000 light-years from end to end, a pair of gargantuan structures glowing with high-energy gamma rays. Discovered in 2010 by NASA, a Fermi Gamma Ray Space Telescope, these faint but immense formations tower above and below our galaxy's disk, dwarfing every other feature in our cosmic neighborhood. If you could see them with the naked eye, they'd span half the night sky. What makes these bubbles so baffling isn't just their size, it's what's inside. They're filled with ultra-fast particles crashing into interstellar gas, generating gamma rays like a cosmic fireworks show. The edges of these bubbles are razor-sharp, as if someone sliced them cleanly out of the surrounding space. And the energy required to create them, unfathomable. We're talking about the equivalent of 100,000 supernova detonating simultaneously. The leading theory points to our galaxy's supermassive black hole, Sagittarius, a star throwing a tantrum millions of years ago. Imagine this: a voracious feeding frenzy as the black hole devoured an enormous gas cloud or even a star. The resulting energy jet, erupting perpendicular to the galactic plane, could have inflated these bubbles like cosmic balloons in a single, cataclysmic event. But here's where it gets weird. There are no signs of such an eruption in the Milky Way's recent history. The bubbles' pristine edges suggest whatever created them happened relatively quickly, yet we found no smoking gun in our galaxy's archaeological record. Another puzzle lies in the particles themselves. The gamma rays we detect require electrons moving at nearly the speed of light, but how they reach such velocities is unclear. Some researchers propose shock waves from the black hole's outburst might accelerate them, while others argue magnetic reconnection, a process where tangled magnetic fields explosively reorganize, could be the culprit. There's even a wild card theory suggesting dark matter annihilation might contribute, though evidence remains thin. What's undeniable is that the Fermi Bubbles rewrite our understanding of galactic ecosystems. They prove our quiet-looking Milky Way has a violent, energetic underbelly, capable of eruptions that reshape its structure on scales we're only beginning to comprehend. And they might not be alone. Similar structures have been spotted in other galaxies, hinting that this could be a universal phase in galactic adolescence. So while these bubbles float silently above us, they're shouting one message loud and clear: our galaxy's past was far more explosive than we ever imagined. We think of black holes as lurking in predictable places, the centers of galaxies, or paired with dying stars. But the Milky Way harbors a far stranger population, rogue black holes, solitary monsters drifting unseen through the void. Current estimates suggest our galaxy might be home to 100 million of these dark wanderers, each the remains of a massive star that collapsed without a trace. Unlike their supermassive cousin at the galactic core, these nomads don't announce their presence with swirling disks of gas or blazing jets. They're invisible, detectable only by the warping of space-time itself as they pass between us and distant stars. Finding them is like playing cosmic hide and seek. When a rogue black hole crosses directly in front of a background star, its gravity bends and magnifies the star's light, an effect called microlensing. For days or weeks, the star brightens in a telltale curve, betraying the black hole's passage. No flash, no explosion, just a subtle distortion in starlight that hints at something massive and unseen. The Hubble Space Telescope has caught a handful of these events, revealing black holes with masses up to 7 times our Sun's, drifting silently a few thousand light-years away. But here's the twist: most rogue black holes don't even give us that clue. Many are dark, no-lensing events, no nearby stars to strip material from. They could be sailing past right now, and we'd never know unless they crossed an unlucky star's path. Some might even be relics of the early universe, primordial black holes formed in the chaos after the Big Bang, hiding in plain sight among their stellar-born cousins. Should we worry? The odds are astronomically slim. Space is overwhelmingly empty. Even with 100 million wanderers, the nearest rogue black hole is likely hundreds of light-years away. A close encounter would spell disaster, warping planetary orbits with its gravity, but the chance of one drifting into our solar system is almost zero. In fact, these black holes might be less dangerous than the stars they once were. At least they're not bathing nearby worlds in lethal radiation, yet their existence reshapes how we see the galaxy. Every microlensing event is a reminder that what we perceive as empty space is anything but, between the stars in the dark we've long ignored, an unseen population of ghosts moves silently through the night. They're the leftover scars of dead stars, the dark punctuation marks in the Milky Way story, and proof that even in our own cosmic backyard, the universe still has surprises to reveal. For over a century, astronomers pictured the Milky Way as a classic spiral galaxy, elegant arms winding outward from a round core, like water swirling down a cosmic drain. But that image shattered when infrared telescopes pierced the dust shrouding our galaxy's heart, revealing a truth far more surprising. Hidden beneath those swirling arms lies a colossal bar, a dense structure of stars stretching 27,000 light-years from end to end, turning our galaxy into what scientists call a barred spiral. This isn't just a subtle tweak to the Milky Way's shape. The galactic bar is a dynamic engine reshaping how stars move across our galaxy. Picture it like a colossal celestial traffic circle, funneling stars into chaotic orbits. While most spiral galaxies have stars gliding smoothly along circular paths, the bar's immense gravity yanks them into elongated, oval trajectories like moths caught in a whirlwind. Near the bar's tips, stars slow down, piling up in what astronomers call orbital crowding, while others get flung outward entirely, adding to the galaxy's spiral arms. It's a gravitational dance that never stops, with the bar acting as both choreographer and disruptor. What's truly astonishing is how this structure pulses over cosmic time. Simulations suggest the bar isn't static. It may grow and shrink rhythmically over hundreds of millions of years, oscillating like a slow cosmic heartbeat. Some studies even hint it could be rotating, creating shock waves that compress gas and trigger bursts of star formation. This might explain why regions near the galactic center show such intense stellar birth activity. The bar's gravitational tides could be squeezing gas clouds like cosmic accordions, forcing them to collapse into new stars. But the biggest mystery lies in how the bar formed at all. One theory points to the Milky Way's messy past collisions with smaller galaxies may have stirred up the inner stars, destabilizing their orbits until they settled into this elongated shape. Others suggest it's a natural phase in galactic evolution, emerging as spiral galaxies mature and their internal dynamics grow more complex. Whatever the cause, its existence forces us to rethink our place in the cosmos. We're not orbiting a serene spiral, we're part of a chaotic, ever-changing structure, riding gravitational ripples we're only beginning to map. So next time you see an artist's rendering of the Milky Way, remember, that central bar isn't just decoration. It's a gravitational powerhouse quietly shaping the destiny of billions of stars, ours included. Nestled in the Milky Way's outer halo, a faint, unassuming star holds the key to our cosmic origins. SMSS J03130.36-670839.3, a name that doesn't exactly roll off the tongue, is the oldest known star in our galaxy, clocking in at 13.6 billion years old. To put that into perspective, it formed when the universe itself was barely a toddler, just 100 million years after the Big Bang. What makes this ancient relic so extraordinary isn't just its age, but what it's missing. Unlike younger stars brimming with heavy elements, this one is almost pure hydrogen and helium with trace amounts of lithium. That absence tells a revolutionary story. The first stars in the universe, called Population 3 stars, were composed solely of these primordial elements. Nothing heavier existed yet. When those pioneers exploded in violent supernova, they forged the first heavier atoms, seeding future generations of stars. But SMSS J03130.36 carries the chemical fingerprint of a very different kind of death. Its minuscule iron content, 10 million times less than our Sun, suggests it formed from the ashes of a single, massive first-generation star that died a quieter death, collapsing directly into a black hole without the usual stellar fireworks. Here's why that matters. Most early stars are thought to have died in pair instability supernova, explosions so powerful they vaporized everything, leaving no remnants. But this star's unique chemistry hints at another pathway, one where some early stars collapsed more gently, preserving pockets of pristine gas that could form second-generation stars like our time capsule here. It's as if we've uncovered a cosmic fossil, a survivor from an era before planets, before galaxies as we know them, even before most elements essential for life existed. Finding SMSS J03130.36 was like spotting a single grain of sand on a beach. Its light is 10 million times fainter than what the human eye can see. Astronomers needed the SkyMapper telescope in Australia and follow-up observations with the Very Large Telescope in Chile just to confirm its identity. But the effort rewrote our understanding of stellar archaeology. Before its discovery in 2014, theorists assumed all first-generation stars died in those catastrophic explosions. Now we know the story's more nuanced, with multiple endings possible in the early universe's dramatic life cycle. What's wild is that this star might not be alone. The Milky Way's halo could harbor hundreds more like it, each a silent witness to the universe's first chapters. They're needles in a galactic haystack, but every one we find adds another piece to the puzzle of how we went from a featureless cosmos to the complex, element-rich universe we see today. So while SMSS J03130.36 might not win any awards for catchiest name, it's earned something far more important, a permanent place in the origin story of everything. Deep in the constellation Centaurus, 5,000 light-years from Earth, a cosmic ghost stretches its icy fingers across space. The Boomerang Nebula holds a record that would make even Pluto shiver. At -458 degrees Fahrenheit, it's the coldest natural place we've ever discovered in the Milky Way, colder than the frigid void between galaxies. This isn't just a pocket of cool gas, it's a realm where physics itself starts to bend. where molecules come alarmingly close to stopping dead in their tracks. What makes this nebula so bone-chilling? The answer lies in its breathtaking expansion. Most nebulae drift outward gently, but the boomerang is practically exploding. Its central star is ejecting material at a staggering 370,000 miles per hour, 100 times faster than a typical nebula's growth. That rapid expansion works like cosmic refrigeration. Picture blowing on hot soup to cool it. The boomerang star is essentially exhaling its outer layers so violently that the gas expands too quickly to retain heat, plummeting temperatures to just 1 degree above absolute zero. But here's where it gets truly bizarre. This nebula shouldn't be this cold. Current models predict such rapid expansion would have slowed by now, allowing background radiation from the Big Bang, which lingers at around -455 degrees, to warm it slightly. Yet the boomerang remains stubbornly colder, defying expectations. Some theorists speculate its central star might have ejected an unusually large mass all at once, creating a superwind that's still cooling exponentially. Others wonder if exotic quantum effects like superfluidity could be at play in the nebula's ultra-dense inner regions. Then there's the nebula's haunting symmetry. Unlike most celestial objects with chaotic, uneven shapes, the boomerang's twin lobes form a near-perfect hourglass likely sculpted by an intense magnetic field or an unseen companion star's gravitational tug. This precision only deepens the mystery. How can something so cold, so violent, also be so beautifully ordered? For now, the Boomerang Nebula remains a cosmic paradox. It's a snapshot of stellar death unlike any other, where the laws of thermodynamics seem rewritten. And as we study its frigid depths, we're reminded that even in a galaxy of blazing stars and scorching plasma, the most extreme places might just be the ones where heat dares not linger. Far out in the Milky Way's swirling arms, drifting between the stars, there's a cloud with an unexpected ingredient: sugar. Not the granulated kind you stir into coffee, but glycolaldehyde, a simple sugar molecule that forms the building blocks for more complex carbohydrates essential to life. Astronomers first detected these sweet molecules in a gas cloud near the center of our galaxy, a region called Sagittarius B2, using radio telescopes capable of picking up the molecule's faint chemical fingerprints. This discovery rewrote our understanding of interstellar chemistry, proving that the precursors to life's key components aren't just earth-bound, they're brewing in the frigid depths of space. What makes these sugar clouds so remarkable isn't just their existence, but how they form. In the near-absolute zero temperatures of interstellar space, chemical reactions should grind to a crawl. Yet on the surfaces of tiny dust grains, something extraordinary happens. Atoms and simple molecules like formaldehyde and methanol stick to these cosmic motes where they slowly jostle and bond. Over millennia, these sluggish interactions build up complex organics piece by piece until full-fledged sugar molecules break free into the surrounding gas. It's chemistry at its most patient, a slow drip process that turns the void between stars into an unlikely candy store. The implications ripple far beyond a quirky cosmic fact. Glycolaldehyde is a direct stepping stone to ribose, the sugar backbone of RNA, a molecule essential for life as we know it. Finding it in space suggests that the raw materials for biology might be scattered throughout the galaxy, hitching rides on comets or asteroids to potentially seed newborn planets. Imagine a young Earth, barren and molten, being pelted by sugar-laden space rocks. Those sweet deliveries could have kick-started the chemical pathways that eventually led to DNA, proteins, and the first living cells. But here's where it gets even wilder. These sugar molecules don't linger alone, they mingle with other prebiotic compounds in molecular clouds, forming a sort of cosmic pantry. Astronomers have spotted clouds laced with amino acids, alcohols, and even the components of cell membranes. Together, they form an interstellar toolkit for life, floating in wait for the right planetary conditions to assemble them into something greater. The hunt for these sweet spots is far from over. With each new generation of telescopes, we're finding more complex molecules in space, some with dozens of atoms intricately linked. And as we map their distribution across the Milky Way, a tantalizing pattern emerges. The galaxy might be dusted with these life-friendly compounds, turning every star-forming region into a potential nursery for chemistry that could one day spark biology. So while we often think of space as empty and lifeless, the truth is far richer. Those dark clouds between the stars, they're not just cosmic backdrops, they're silent kitchens brewing the ingredients that might one day stir to life under the light of an alien sun. The universe, it seems, has a sweet tooth, and that changes everything. For centuries, the Milky Way's spiral arms seemed like fixed features, permanent cosmic ridges where stars clustered like beads on a string. But modern astronomy has uncovered a strange truth. Some of those arms might be cosmic mirages, fleeting patterns in the stellar sea rather than solid structures. These phantom arms emerge from a phenomenon called density waves, ripples of compressed gas and stars that move through the galaxy like traffic jams in a cosmic freeway. Imagine cars briefly bunching up on a highway, then dispersing, except here, the cars are stars and the highway spans light years. The Gaia Space Telescope's 3D maps revealed the illusion in stunning detail. While some arms are indeed dense with stars moving together, others appear only because stars are momentarily piling up as they orbit at different speeds, creating the impression of a continuous structure. It's like watching a crowd in a stadium wave. From a distance, the wave seems like a solid ripple, but up close, you see individuals standing and sitting at just the right time to create the illusion. In the Milky Way's case, these phantom arms are regions where stars slow down, crowding together before speeding up again, leaving the pattern intact even as the stars themselves drift apart. But not all arms are imaginary. Gaia confirmed at least two major spiral arms with physical staying power, the Scutum Centaurus and Perseus arms, where stars, gas, and dust are genuinely bound together by gravity. These are the galaxy's true backbone, massive enough to shape the orbits of everything around them. The difference lies in longevity. Phantom arms might last a few 100 million years before dispersing, while the real structures persist for billions of years, acting as anchors in the galaxy's ever-shifting dance. The wildest part, we're caught in one of these illusions right now. Our solar system currently orbits through the Orion Spur, a minor arm once thought to be a permanent feature. Gaia's data suggests it might just be a local overdensity, a stellar traffic jam we're passing through, destined to dissolve over time. This reshapes how we see our place in the galaxy. Instead of living in a fixed neighborhood, we're temporary passengers in a dynamic, evolving structure where even the grandest patterns are in constant flux. What's emerging is a picture of the Milky Way as a living, breathing entity, its spiral arms flickering in and out of existence like ripples on a pond. Some are deep gravitational features, others are fleeting tricks of celestial perspective. And with every new Gaia data release, we're learning to tell the difference, one star's motion at a time. Beyond the familiar glow of the Milky Way's spiral arms lies a hidden frontier, the galactic halo, a vast and turbulent ocean of hot gas stretching hundreds of thousands of light years into the void. This isn't some serene cosmic backdrop. It's a maelstrom of superheated plasma, with temperatures soaring into the millions of degrees and gas clumps hurtling at wildly different speeds. Recent X-ray observations have peeled back the veil on this chaotic region, revealing a dynamic ecosystem where the Milky Way breathes, expelling and reabsorbing material in a cycle that could shape its future. The halo's violence comes from the galaxy's own metabolism. Supernova and stellar winds blast gas outward at breakneck speeds, while matter from ancient cannibalized galaxies rains down in fiery streams. The result, a churning, unpredictable environment where pockets of gas move so fast they could escape the Milky Way entirely, while others loop back in colossal fountains. NASA Chandra X-ray Observatory has mapped these motions, catching glimpses of gas clouds moving at nearly 2 million miles per hour, fast enough to cross the continental United States in under 2 seconds. But the halo isn't just a dumping ground for galactic exhaust. It's a recycling plant on a cosmic scale. Some of that ejected gas, enriched with heavy elements from stellar explosions, eventually cools and falls back toward the disk, fueling new generations of stars. This process, called galactic feedback, acts like a thermostat for star formation. Too much outflow, and the galaxy starves itself of material. Too little, and it risks burning through its fuel too quickly. The Milky Way's halo strikes a delicate balance, regulating the pace of stellar birth across eons. What's truly baffling is how lumpy this system is. Instead of a smooth, even distribution, the halo contains bizarre clumps and filaments, some spanning tens of thousands of light-years. One leading theory suggests these are echoes of past galactic mergers. The shredded remains of dwarf galaxies digested long ago, their gas still swirling in the Milky Way's gravitational grip. Others propose they're bubbles from ancient bursts of activity near the supermassive black hole, now rising through the halo like smoke rings from a cosmic chimney. This hyperactivity has profound implications for the galaxy's future. Simulations show that without this energetic halo, the Milky Way's star-forming gas would have been depleted billions of years ago. Instead, the constant churn ensures fresh material keeps cycling back, sustaining star birth far longer than expected. Yet it's a fragile equilibrium. Too much turbulence could eject gas permanently, leaving the galaxy to fade into a quiet, aging state. Too little, and it might exhaust its fuel in a blaze of unchecked star formation. So while the halo might seem like a distant afterthought, it's anything but. It's the Milky Way's pulse, its respiratory system, and perhaps its destiny, all written in the seething, invisible storms that rage beyond the light of stars. And as we learn more about this hidden frontier, we're uncovering the invisible forces that don't just surround our galaxy, but sustain it. Out in the depths of the Milky Way, orbiting a star 11,000 light-years away, there's a world that shouldn't exist. Meet Kepler 1625b, the first candidate exomoon ever detected, and a cosmic rule breaker that's left astronomers scratching their heads. This isn't just any moon, it's a behemoth, dwarfing every satellite in our solar system with a size and mass comparable to Neptune itself. Picture a gas giant-sized moon circling another gas giant, a planetary pairing so bizarre it defies everything we thought we knew about how moons form. The discovery sent shockwaves through the astronomy community because, according to current models, moons this massive simply can't exist. In our own solar system, moons form one of two ways. Either they coalesce from debris left over after planet formation, like Earth's moon, or they're captured asteroids or dwarf planets, like Mars's irregularly shaped Phobos and Deimos. But Kepler 1625b shatters both scenarios. A gas giant moon couldn't form in place from a planet's debris disk. There's not enough material. And capturing a Neptune-sized object, the gravitational gymnastics required make it statistically laughable. Yet there it is, lurking in the data. Astronomers first spotted its fingerprints in the subtle dimming of its host star, Kepler 1625. When the planet passed in front of the star, it caused the expected dip in light, but then came a second, smaller dip shortly after, as if something trailing the planet was blocking starlight too. Further analysis of the system's gravitational wobbles suggested an object roughly 1.5% the mass of its host planet, a telltale signature of a moon, but on a scale no one predicted. The implications are staggering. If this moon is real, and some researchers still debate its existence, it forces us to rewrite the playbook on planetary formation. One radical theory suggests it might be the remnant core of a failed planet, a world that started forming in the protoplanetary disk but got swallowed by its larger neighbor before it could grow to full independence. Another posits it could be the survivor of a catastrophic collision between two gas giants, a cosmic accident so rare we might never see another like it. Or perhaps it's evidence of an entirely new formation mechanism, one we've yet to imagine. What's undeniable is how this discovery humbles us. For centuries, we've treated our solar system as a template, assuming moons would follow familiar patterns. But Kepler 1625b laughs at those assumptions, proving the universe is far stranger and far more creative than our theories can predict. And if this moon exists, what other impossibilities are waiting in the dark, ready to upend our cosmic expectations? Scattered across the Milky Way like cosmic smoke rings, mysterious circles of radio energy hover in space, ghostly structures so vast they could swallow entire solar systems. Discovered in 2020 by Australia's ASCAP telescope, these odd radio circles, or ORC, defy easy explanation. Each one spans hundreds of thousands of light years, emitting faint radio waves but remaining invisible in every other wavelength. They linger like echoes of some unimaginable explosion, and their origins have astronomers locked in a spirited debate. The leading theory points to supermassive black holes throwing tantrums on an epic scale. When black holes feed, they sometimes belch out twin jets of energy at near light speed. If one of these outbursts occurred millions of years ago, its shockwaves might have plowed through intergalactic gas, leaving behind these expanding bubbles of radio emission. But there's a hitch. Most ORCs appear isolated, with no obvious black hole at their center to blame. Some could be the ancient remnants of mergers between black holes, a final rippling scream of gravitational energy frozen in space. Others might trace the edges of galaxies we can't even see, their radio glow marking where a dwarf galaxy's gas collided with the Milky Way's halo. Then there's the wild card. ORCs might represent something entirely new. One provocative hypothesis suggests they're the fingerprints of cosmic strings, hypothetical defects in space-time left over from the Big Bang. If these threads of pure energy vibrate or snap, they could unleash bursts of particles that create these ghostly rings. Another idea posits they're the aftermath of dark supernova, theoretical explosions from stars made of exotic matter we've yet to discover. The sheer scale of ORCs hints at energies beyond anything we've observed, as if the universe is flaunting phenomena we don't yet have the vocabulary to describe. What makes these rings even stranger is their structure. Unlike supernova remnants which fade unevenly, ORCs are eerily symmetrical, perfect circles hanging in space like cosmic bullseyes. That symmetry suggests an explosion propagating uniformly in all directions, but the energy required would dwarf even the most violent known events. Some researchers wonder if multiple ORCs could be overlapping, creating the illusion of pristine rings when in reality they're the tangled wreckage of multiple cataclysms. For now, the mystery deepens with each new observation. Recent studies have found some ORCs emitting faint X-rays, while others seem linked to distant galaxies undergoing violent star formation. Every clue adds another layer to the puzzle, reminding us that even in our own backyard, the Milky Way still holds cosmic riddles we're only beginning to frame. Whether they're the graves of black hole eruptions or windows into new physics, one thing's certain: these radio rings are whispering secrets from the edge of our understanding, and we're just starting to listen. Rising from the Milky Way's core like twin titanic fountains, colossal geysers of superheated gas blast outward at millions of miles per hour, cosmic plumes so powerful they could fill the distance between Earth and the Moon in less than a minute. These aren't your average stellar winds. They're galactic scale outflows stretching 50,000 light-years above and below the galactic plane, carrying enough energy to shape the destiny of our entire galaxy. If Yellowstone's Old Faithful were scaled up to celestial proportions, it wouldn't even register next to these monstrous eruptions. What fuels such unimaginable violence? The leading suspects are our galaxy's most energetic residents. Near the Milky Way's heart, frenzied star formation births massive stars that live fast and die violently, their combined supernova creating hurricane-force stellar winds. Meanwhile, our supermassive black hole, Sagittarius A star, occasionally feeds on wayward gas clouds, spearing space with jets of plasma that could kickstart these outflows. The truth likely involves both a cosmic tag team where star formation provides the initial push, while black hole activity amplifies the turbulence to unbelievable extremes. The sheer scale of these geysers rewrites our understanding of galactic ecosystems. Containing enough gas to form millions of stars, they act like a pressure valve for the Milky Way, ejecting material that might otherwise fuel too many new stars too quickly. Observations from the Hubble Space Telescope reveal their structure in stunning detailed tendrils of charged particles twisted by magnetic fields, glowing in X-rays as they collide with the galaxy's halo gas at temperatures hotter than the Sun's core. Some of this material rains back down in cosmic recycling streams while the rest escapes forever, lost to the intergalactic void. Here's where things get weird. Unlike the symmetrical Fermi bubbles these geysers carved through earlier, their shapes are chaotic and asymmetrical, as if something disrupted their flow. Astronomers suspect past galactic mergers might be to blame, with incoming dwarf galaxies distorting the outflows like rocks diverting a river. There's even evidence that our galaxy's magnetic field, normally invisible, becomes briefly detectable where these geysers rage, their turbulence making the field lines glow in radio waves like cosmic neon signs. What's truly humbling is realizing we're witnessing a process that shapes galaxies across the universe. These aren't just local oddities, they're part of how galaxies regulate their growth, balancing star birth and death on scales we're only beginning to comprehend. And as we study their flickering light, we're catching glimpses of the Milky Way's fiery breath, a reminder that even seemingly quiet galaxies like ours harbor unimaginable power just beneath the surface. Deep in the atmospheres of ice giants like Neptune and Uranus, a storm of diamonds may be falling not as glittering gems, but as a relentless hail of crystallized carbon. This bizarre phenomenon, known as diamond rain, begins with methane, a simple molecule of one carbon atom bonded to 4 hydrogens. Under the crushing pressures found tens of thousands of miles below these planets' cloud tops, methane shatters, its hydrogen stripped away by forces equivalent to stacking 500 jumbo jets on a single coin. The freed carbon atoms, desperate to find stability, bond together in tetrahedral lattices, forming microscopic diamonds that plummet through layers of slushy ice and compressed gases like tiny celestial bullets. Scientists first theorized diamond rain in the 1980s, but it wasn't until 2017 that they recreated the conditions in a lab. Using the world's most powerful X-ray laser at SLAC National Accelerator Laboratory, researchers blasted polystyrene, a methane stand-in, with shockwaves reaching nearly 1.5 million times Earth's atmospheric pressure. In nanoseconds, they watched carbon atoms rearrange into diamond structures, proof that nature might be running the same experiment on a planetary scale. The diamonds they observed weren't the flawless stones of a jeweler's display. They'd be more like gritty nanodiamonds, likely accumulating in thick layers around the planet's cores over billions of years. What makes this discovery revolutionary isn't just the spectacle, it's the energy dynamics. As diamond rain sinks, it releases gravitational energy, potentially heating Uranus and Neptune's interiors by thousands of degrees. This could explain why these ice giants radiate more heat than expected. Their diamond downpours might be literal buried treasure, slowly releasing thermal energy as they descend. Some models even suggest entire layers of liquid diamond oceans could exist near these planets' cores, with solid diamond icebergs floating atop them, a landscape so alien it defies earthly comparison. Now imagine this process scaled across the galaxy. Exoplanets with methane-rich atmospheres, especially hot Neptunes orbiting close to their stars, could experience diamond rain at even more extreme rates. Their higher temperatures might allow diamonds to form higher in the atmosphere, creating glittering storms visible from space. There's tantalizing evidence from planets like WASP-12b, where astronomers have detected excess carbon that could hint at such processes. If diamond rain is common, it means the universe isn't just making these precious stones in supernova explosions or crushing dwarf stars. It's manufacturing them inside countless planets, then burying them forever in unseen depths. Think of it, entire celestial bodies might have diamond layers thicker than continents, hidden beneath swirling clouds, but don't expect interstellar mining expeditions anytime soon. These diamonds aren't just inaccessible, they're trapped in environments so hostile they'd vaporize any probe instantly. Yet their existence reshapes how we see planetary chemistry, proving that even familiar elements like carbon can behave in ways that turn planetary science into something resembling alchemy. The universe, it seems, has a flair for the extravagant, turning gas giants into cosmic jewelers, crafting treasures no one may ever see. Deep in the constellation Coma Berenices, astronomers stumbled upon a cosmic paradox, Dragonfly 44, a galaxy that shouldn't exist. It's the size of the Milky Way, weighing in at a staggering 1 trillion solar masses, yet it emits less than 1% of the starlight our galaxy does. This isn't just a dim galaxy, it's a ghost, an almost starless void where darkness reigns supreme. Welcome to the eerie world of dark galaxies, shadowy structures that could rewrite our understanding of how the universe builds its largest creations. What makes Dragonfly 44 so unsettling is its composition. While normal galaxies like ours are studded with glittering stars, this one is a vast sea of nearly nothing, with barely enough stars to dot its expanse. The rest of its mass, almost entirely dark matter, the mysterious substance that outweighs visible matter 5 to 1 in the cosmos. Here, that ratio skews even more extreme. 99.99% of this galaxy's mass is invisible, making it one of the purest dark matter laboratories in the known universe. The discovery of dark galaxies turns conventional astronomy on its head. Traditional models assume that dark matter's gravitational pull brings gas together, triggering star formation. But in places like Dragonfly 44, something went wrong, or perhaps something we don't yet understand. Maybe the gas was too spread out, never reaching the density needed to ignite stars. Or perhaps some ancient event, a collision, a quasar's blast stripped away the galaxy's star-forming fuel eons ago, leaving it frozen in embryonic darkness. Yet the real shock came when astronomers studied Dragonfly 44's motion. Despite having almost no stars, its remaining stars orbit at speeds that should fling them into the void, unless an immense halo of dark matter anchors them in place. That's when the truth became clear. This galaxy isn't broken. It's a dark matter factory operating exactly as designed, proving that galaxies can form around invisible scaffolds with stars as mere afterthoughts. The implications ripple far beyond this single ghostly galaxy. If structures like Dragonfly 44 are common, it means we've been missing a hidden layer of cosmic architecture, entire galaxies hiding in plain sight, detectable only by their gravitational whispers. Some theorists speculate these dark galaxies could be the universe's missing links, primordial structures that never quite sparked to stellar life. Others wonder if they're the skeletons of failed galaxies, doomed by their inability to retain gas. But here's the most tantalizing possibility. Dark galaxies might solve one of astronomy's biggest puzzles, the missing satellites problem. If many of the Milky Way's predicted dwarf galaxies are actually starless, cloaked in darkness, it would explain why our telescopes see so few of them. They're not missing, they're just invisible, lurking silently at the edges of our cosmic neighborhood. As telescopes grow more sensitive, more of these shadowy giants may emerge from the black. Each one is a Rosetta Stone for dark matter, a place where its fingerprints aren't obscured by the glare of stars. And as we decode their secrets, we're forced to confront a humbling truth. The universe doesn't just build galaxies we can see. It crafts entire worlds of shadow, vast and silent, spinning through the night without a single light to betray their presence. Scattered like frozen fireflies around the Milky Way's halo, globular clusters hold memories older than the dinosaurs, older than Earth itself. These dense, spherical swarms of stars aren't just pretty cosmic ornaments. They're time capsules preserving the galaxy's chemical infancy in stellar amber. While most stars in the Milky Way's disk recycle material through generations of births and deaths, globular clusters remain pristine vaults, their stars locked in a cosmic deep freeze for over 12 billion years. Each cluster is a snapshot of the universe's childhood, a window into an era when the Milky Way was just assembling itself from primordial gas. Take Messier 92, one of the oldest known clusters, where stars burn with barely a trace of elements heavier than helium. That absence speaks volumes. In the early universe, only hydrogen, helium, and a whisper of lithium existed. Heavier elements, carbon, oxygen, iron hadn't yet been forged in stellar furnaces. So when Messier 92 stars formed, they crystallized from nearly pure primordial material. Studying them is like finding untouched parchment from the universe's first chapter, before supernova began scribbling heavier elements across the cosmos. Their composition reveals what the Milky Way was built from the raw ingredients before cosmic cooking began. But the real surprise came when astronomers noticed not all globular clusters are chemically identical. Some, like Omega Centauri, contain stars with slightly richer metal content, hinting at multiple generations of star birth. This defied expectations, since clusters were thought to form all their stars in one furious burst. The discovery suggests these structures might be the mangled remains of dwarf galaxies devoured by the Milky Way, their stars compressed into clusters during the chaos of collision. Omega Centauri's unusual size and motion support this. It behaves less like a native cluster and more like the survivor of a galactic demolition. What's astonishing is how much these clusters remember. By measuring the subtle variations in their star's light, astronomers can reconstruct their orbits over billions of years, tracing paths that reveal the Milky Way's growth through cosmic time. Some clusters, like NGC 6709, orbit backward compared to the galaxy's spin, a celestial relic of the violent mergers that shaped our galactic home. Others, like Palomar 5, are slowly being torn apart by tidal forces, leaving shimmering trails of stars' ghostly breadcrumbs marking the Milky Way's gravitational grip. Yet the greatest mystery lies in their resilience. How have these clusters survived so long, resisting the gravitational turbulence that should have ripped them apart? The answer might lie in their incredible density, with stars packed so tightly near the core that 1 million could fit between us and Alpha Centauri. That density creates a gravitational fortress, shielding the clusters from external chaos. Some even harbor hidden black holes at their hearts, acting as anchors to stabilize the stellar swarm. As we decode these ancient stellar archives, one truth becomes clear. Globular clusters aren't just bystanders to the Milky Way's history, they're active participants. Their very existence hints at the violent processes that built our galaxy, from cannibalized dwarf galaxies to primordial gas collapsing in the universe's dawn. And as telescopes peer deeper into their hearts, we're not just studying stars, we're reading the autobiography of the cosmos itself, written in the glow of its oldest survivors. High above the Milky Way's plain, floating in the constellation Monoceros, there's a cosmic anomaly that looks less like a nebula and more like a piece of abstract art, the red rectangle. At first glance, its sharp, geometric perfection seems impossible. Most nebulae are chaotic swirls of gas, sculpted by explosive stellar winds or the random collapse of molecular clouds. But this one, it's a near-perfect X shape with ladder-like rungs of glowing dust stretching between its arms, as if drawn by some celestial architect with a ruler and protractor. The secret to this impossible geometry lies in its heart. Not one star, but two. HD 44179, a binary system, sits at the nebula's center, locked in a gravitational dance so precise it's essentially spraying gas into space like a spinning lawn sprinkler. As the stars orbit each other every 10 months, they channel their stellar winds into twin jets that carve out the nebula's bizarre structure. Typically, such outflows would create a messy, uneven shape. But here, a dense disk of dust surrounds the stars, acting like a stencil. The jets can only escape perpendicular to the disk, funneling material into those crisp, angular lanes. The result, a cosmic etch-a-sketch where stellar mechanics conspire to create one of the most unnatural-looking sights in the galaxy. Even the nebula's eerie red glow defies explanation. Most emission nebulae shine pink or blue, energized by young, hot stars. The red rectangle, though, owes its crimson hue to an exotic form of carbon-rich dust. These aren't ordinary soot-like particles, they're complex organic molecules called polycyclic aromatic hydrocarbons, or PAR, which fluoresce under ultraviolet light like neon signs. But there's a twist. The way these molecules are arranged stacked in unusually ordered layers creates a phenomenon called extended red emission, amplifying the nebula's ruby glow far beyond what typical dust should produce. It's as if the dust itself is engineered to enhance the spectacle, turning the entire structure into a cosmic light show. Theories abound about how such precision emerged. One camp argues the binary star's unique orbit, slightly elongated, but not quite elliptical, generates resonant frequencies that shape the outflow like sound waves molding sand on a vibrating plate. Others point to the dust disk's bizarre properties. Its particles might be unusually sticky, clumping into larger grains that behave more like construction beams than fine powder. Then there's the wild card. Some researchers speculate the system underwent a recent, violent event, perhaps a near miss with another star, that abruptly altered its dynamics, freezing the nebula in this unnatural state before chaos could reclaim it. Whatever the cause, the red rectangle stands as a reminder that nature's creativity knows no bounds. It challenges our assumptions about how structure forms in the universe, proving that even in the cold vastness of space, there's room for the uncannily perfect. And it won't last forever. In a few thousand years, the star's winds will dissipate the dust, erasing this cosmic masterpiece like a sandcastle at high tide. For now, though, it lingers, a fleeting monument to the universe's capacity for precision, and a puzzle we're only beginning to decode. Imagine you're lost in the Milky Way, untold light years from home with no familiar stars to guide you. No problem, just tune into the Cosmos Natural Lighthouse Network, pulsars. These spinning neutron stars emit beams of radiation with metronome-like precision, some ticking more accurately than atomic clocks. Their rhythmic flashes create a celestial Morse code, unique to each pulsar based on its spin rate. For an advanced civilization or even future human explorers, these cosmic beacons could form the ultimate interstellar GPS, a navigation system written across the galaxy itself. The idea isn't science fiction. In 1972, NASA etched the first galactic roadmap onto the Pioneer plaques, followed by pulsar maps on the Voyager golden records. These diagrams used 14 nearby pulsars as reference points, with each line pointing toward a pulsar and binary code denoting its frequency. The math was elegant. Any species encountering the spacecraft could trace the pulsar's positions back to our solar system, like following breadcrumbs home. What's wild is that these maps remain accurate for millions of years. Pulsars are so stable that their slow spin-down rates barely affect their timing over human timescales. But why pulsars? Unlike stars, which blur together across cosmic distances, each pulsar has a distinct fingerprint. Some spin hundreds of times per second, others lumber along at glacial paces. Their radiation penetrates dust clouds that obscure visible light, making them detectable from anywhere in the galaxy. And here's the genius part: you wouldn't even need a map like ours to use them. By measuring slight variations in pulse arrival times as you move through space, you could triangulate your position in 3 dimensions, adjusting course in real time. It's like celestial dead reckoning, with the universe itself providing the signals. The implications are staggering. Civilizations separated by thousands of light years could share a common coordinate system without prior contact, anchoring their maps to these natural clocks. Some theorists speculate that advanced societies might even enhance pulsars for navigation. Imagine a network of artificially stabilized neutron stars, their beams modulated to carry additional data. Far-fetched maybe, but consider this: we've already found pulsars in binary systems with orbits so precise they rival our best atomic clocks. Nature, it seems, has done half the engineering work for us. So while we're still tethered to Earth's GPS satellites, the blueprint for galactic wayfinding floats out there in the void, ticking away patiently. Those flashes aren't just cosmic curiosities, they're signposts waiting for travelers bold enough to read them. And someday, whether it's us or someone else, the Milky Way's heartbeat may guide explorers home. Right now, the Milky Way sails through the cosmic void in deceptive solitude, but its days as a lone island of stars are numbered. 4 billion years from now, our galaxy will commit the ultimate act of celestial cannibalism, colliding headfirst with its colossal neighbor, the Andromeda Galaxy. This isn't some distant hypothetical, it's a cosmic certainty, set in motion by the relentless pull of gravity. Hubble's Space Telescope measurements confirm the 2 galaxies are closing the gap at 250,000 miles per hour, a slow-motion car crash spanning eons. And when they meet, the night sky will transform into something unrecognizable. Picture this as the galaxies first brush past each other. Their mutual gravity stretches them like taffy, warping their spiral arms into long, shimmering tidal tails of stars. Andromeda, twice the Milky Way size, will dominate the dance, its immense gravity yanking stars from our galaxy into dazzling arcs across the heavens. From Earth, if it still exists, the sky would blaze with the light of newborn stars as colliding gas clouds ignite a firestorm of star formation. For billions of years, the 2 galaxies will loop around each other in a chaotic waltz, their stars mingling like swarms of fireflies caught in a hurricane. Yet here's the cosmic irony: despite this cataclysm, actual stellar collisions will be vanishingly rare. The distances between stars are so vast that even as galaxies merge, stars will mostly slip past one another unscathed. It's the emptiness of space that saves them. Imagine 2 crowds of people running together where each person is 1,000 miles apart, the real victims. The delicate structures of the galaxies themselves, spiral arms will shred, dust lanes scatter, and orderly orbits dissolve into chaos. Over time, the Milky Way and Andromeda will forget their original shapes entirely, merging into a single, bloated elliptical galaxy astronomers dub Milkdromeda, a bland, featureless orb of aging stars. But the drama doesn't end there. Simulations suggest the merger will kick many stars into intergalactic exile, flung out by gravitational slingshots into the endless dark. Others will plunge toward the newly merged supermassive black holes at the galaxy's cores, feeding a quasar brighter than 1,000 supernova. And lurking in the background, the Triangulum Galaxy, our 3rd largest neighbor, might join the fray, turning a duet into a chaotic trio. What's humbling is realizing this apocalypse has already begun in cosmic terms. The light we see from Andromeda tonight left when Earth's continents were still forming. By the time the collision starts, the sun may have swelled into a red giant, swallowing our planet long before the galaxies do. Yet the universe doesn't rush for anyone. This dance of giants unfolds on timescales that dwarf human history. a reminder that even galaxies aren't permanent, just waypoints in an ever-evolving cosmos. So while the Milky Way's fate is sealed, its legacy will live on, rewritten in the stars of Milkdromda, a testament to the impermanence of all things, even the heavens themselves. From ghostly dark matter halos to cosmic diamond rain, from rogue black holes to the Milky Way's impending collision with Andromeda, our journey through these galactic secrets reveals a universe far stranger than we ever imagined. We've seen how our galaxy hides entire populations of runaway stars, unexplained radio rings, and stellar fossils older than Earth itself. Yet for every mystery we've uncovered, a dozen more lurk in the shadows, waiting to rewrite the rules of astrophysics. Think about this: we live inside the Milky Way, yet we're still mapping its shape. We've discovered structures like the Fermi Bubbles towering over us, but we don't fully understand what created them. We've detected sugar molecules floating between stars, but can't say for certain how widespread life's building blocks might be. Even something as fundamental as dark matter, the invisible glue holding our galaxy together, remains almost completely unknown to us. That's the humbling truth. The more we learn about our cosmic home, the more we realize how much we don't know. But that's what makes astronomy so thrilling. Every new telescope, every space mission, every night of stargazing could reveal another piece of the puzzle. Maybe you'll be the one to spot an odd radio circle in fresh telescope data, or help explain why some globular clusters shouldn't exist based on our current models. The galaxy isn't just a collection of stars, it's an ongoing story, and we're all part of writing it. So tonight, when you step outside and look up at that shimmering band of light arching across the sky, remember, you're not just seeing stars. You're gazing at rogue planets made of diamond, at ancient stellar graveyards, at invisible forces sculpting the cosmos on scales beyond human comprehension. Which of these galactic secrets left you the most awestruck? Drop your favorite in the comments. I'd love to hear what amazed you most about our incredible Milky Way. And keep looking up, because the next great discovery might be hiding in plain sight, just waiting for someone to